Hi, we are in module 46 now. In this module what we are going to look at is, we are going to look at different kind of assignments that is there in Verilog. So I am taking this slight detour, and in module 47 I will connect pipelining with Verilog. So we have been doing some bit of black magic all along. Right? So the material that I am going to present here is partly based on Stuart Sutherland's material on understanding Verilog blocking and non-blocking assignments. Some of the examples are taken from his material and some of the examples are made otherwise. So in Verilog we have been doing a bit of this black magic. So there were multiple assignments and I was using equal to versus this token less than or equal to, or this less than symbol followed by equal to at different places, right, without explaining what they are actually doing. So in this video I will explain what these different statements are and the implications of these statements. So first of all, assignments in Verilog are of two different kinds. There is something called continuous assignment, there is something called procedural assignment. The continuous assignment is something that happens outside of always statements and outside of initial blocks. So primarily all the assignments that you do with assign statements are actually continuous assignments, or anything that you do with instantiation of logic which you connect to other wires is also a continuous assignment. So the left side of a continuous assignment is usually declared as a wire, and wires can have only one continuous assignment. It is usually done with equal to. So you know all of these statements, right? Assign A equals B and C. So when you do that, the assign is the keyword. So A is the variable on the left side, A should be declared as a wire, and you can have only one assign A equals A plus B or A and B. You cannot have assign A equals A and B and also another assign A equals A and C. You cannot do that, because what that would mean is there are two different gates that are driving the same wire. That is not acceptable. So wires can have only one continuous assignment that is assigning to it. The assignment is done with equal to. You cannot use less than and equal to token for this. So example is assign sum equals A XOR B, right. So sum is supposed to be declared as a wire. This is a continuous assignment statement, this is a continuous assignment operator, and there is an expression on the right side, right. So this is called continuous assignment. Whereas procedural assignments are those that happen inside procedural blocks. The procedural blocks that we have seen so far are initial statements, which is not very useful other than test benches, but always blocks are procedural statements. So this is equivalent to procedures as we know in sequential programming languages. So let me take a small detour and look at procedural assignment statements. So we are talking about procedural assignment statements. There are two kinds of procedural assignment statements. The first kind is called blocking, the second kind is called non-blocking. So the first kind, blocking, is essentially done with equality symbol. So you can see that here in the examples. Let me come to that in a little while. So the first thing is a blocking assignment is an assignment that happens within a procedural block. So always is a procedural block. An assignment that you do with equal to inside an always block is called a blocking assignment. So a blocking assignment happens in this form. The assignment must complete before the next line is executed. So let us look at this procedural block. If I look at this statement, there is something on the left side, we are saying is equal to something on the right side, right. What that means is, until I execute the blue line, this red line will not get executed. So this is similar to how your sequential programming languages work. If I write a 10-line program, the line 1 must execute before line 2 and line 2 must execute before line 3 and so on, right. So if I put this equality symbol, what that means is I have to execute this line before I execute this red line. The same thing is true here also. I have to execute the blue line before I execute the red line, and more importantly, always this red line's execution follows the blue line's execution. So if I have 5 lines of code, line 1 will get executed before line 2. So, this is the notion of a procedural assignment. In a procedure, if I have 5 lines, then line 1 should get executed before line 2, line 2 before line 3 and line 3 before line 4 and so on. And the assignments, if they are using blocking assignment, which is done using equal to, then the execution of the flow is blocked until the assignment is complete. So, now let us take a look at this example. I will explain what this implication of a blocking assignment is. Let us say I want to take a 16-bit bus and I want to swap the contents of the bus. What I want to do is I want to take the top half of the bus, put it in the lower half, and take the lower half and put it in the upper half. So, let me draw a picture of what I want to do. So, I have a bus that is coming in. So, let us look at this picture here. So, I have a bus that is coming in. So, this is a bus that has 15 to 8 and this is a bus which has 7 to 0. What I want to do, the problem statement is I want to swap the contents of the bus. This is what I want to do. So, this is still 15:8, this is still 7:0, but what I want is when the clock pulse comes, I want 7 to 0 to appear in 15 to 8 and 15 to 8 to appear in 7 to 0. So, this is the problem statement. For this problem statement, let us look at this piece of code that I have written. Right. So, in this piece of code, I have always at passage of clock. You know that if I do always at passage of clock, when the clock pulse comes in, these actions are supposed to be run. Right. How are these actions going to be executed? First of all, it is a procedure. So, the first line will get executed before the second line. So, the blue line will get executed before the second line, right, the red line. So, let us look at the blue line. In the blue line, according to, so the assignment that you have is a blocking assignment. What that means is you take word 7:0, you assign it to 15:8. Until that assignment is over, you cannot go to the red line, which means word of 7:0 is copied on to 15:8, right. So, I wanted things to be swapped. So, word of 7:0 got copied on to 15:8. Now, when I refer to word 7:0, it has already taken a new value. Because of that, this word of 7:0 is taking the new value of word of 15:8. So, whenever you see a equal to, right, of this kind, you think of this side as the old one and this side as the new one. So, this is old value of 7:0, this is equality symbol, and this is value of word 15:8. So, the old value of 7:0 becomes the new value of 15:8, but because it is a blocking assignment, the new value of 15:8 will appear here, because unless this statement's assignment is over, the red line cannot execute, which means this 15:8 will appear here as 15:8, the new value appears here and that gets copied to 7:0. So, let us see the implication of it. So, what I want is, let us look at this picture again. We have this is what we wanted. As a sequence, what we did was word of 15:8 we said is equal to word of 7:0, and we said word of 7:0 is equal to word of 15:8. Let us see the implication of this. So, this one is a blocking assignment. So, what it does is, so you want, this is the output 15:8 and this is the output 7:0, and these are the two inputs. This is 15:8 and 17:0, and we are designing a black box. We are designing a circuit for this, right. So, what this does is 7:0 gets copied to 15:8, right. So, 7:0 is ready to copy to 15:8. So, that is what this assignment does, but because it is blocking, this value 15:8 is immediately available for the next statement. And what is this going to be? So, this is going to take whatever value of 15:8 is, and what is the value of 15:8 now? It is this value, right. It takes this value and gives it to 7:0. So, what this has essentially done is, it is not swapping 15 colon 8 and 7 colon 0. It did not do that. Instead, the 7 colon 0 is copied on both the half of the buses. So, again if you go back to the slides, this left half, this always block is incorrect, because at the end of this clock pulse both 7 colon 0 and 15 colon 8 will have the old value of 7 colon 0. Before the clock pulse came, whatever was there at 7 colon 0, that will appear in both the top half and the bottom half. If I change the order around, that is what I have done in this picture. So, in the right side I have done that. So, I have put word of 7 colon 0 line before the word of 15 colon 8 line. So, this is not going to be any different. What it is going to do is, whatever was there before the clock pulse came in at 15 colon 8, those 8 bits, it will take that and put it in both 7 colon 0 and 15 colon 8. So, this is the meaning of blocking assignment. A blocking assignment is one in which, first of all, it is inside a procedural block like an always block. So, an equality symbol that is in the assignment statement, assign statement, is not a blocking assignment, it is a continuous assignment. An equality symbol within an always block is a blocking assignment. The moment you see a blocking assignment, the way you should think about that is, whatever you is in the right side of it will be immediately available to the left side, and any subsequent use in the following lines will use that new value that was assigned. So, that was the problem here, and this is not helping us swap. I still want to be able to swap the contents of the top half and the bottom half. For that, I can do something called non-blocking assignment. The first thing I want to show is what is in the bottom. Let us look at the always blocks that is written up. So, instead of equality equal symbol token, we have put less than equal to. So, that is less than followed by equal to. We have put 2 tokens, less than equal to, in both these places, and my claim is that this always block as well as this always block will actually swap the contents of the top half and the bottom half of the buses, right. So, let us see how this is done. First of all, any non-blocking assignment. So, the word non-blocking means this assignment should not block the assignments that are following the assignment. So, what that means is, this is a non-blocking assignment, this blue line is a non-blocking assignment, but this non-blocking assignment should not itself block the execution of the red line. So, the blue line being above the red line should not block the execution of the red line. That is the meaning of non-blocking assignment. So, let us take this a little slowly. It's non-blocking assignments are evaluated and assigned in 2 steps. In blocking, as soon as the evaluation is over, you assign it to the left side, whereas in non-blocking the evaluation happens independently and the assignment happens independently. The first thing is, the right side is evaluated immediately. So, if you go and look at this part, the right side is word 7 colon 0 and word 15 colon 8. Evaluating that means, in some sense you get a copy of those 2, right. You will do this for all the non-blocking assignments that are on the right side. So, when you look at this sequence of statements, the right side is evaluated immediately and the assignment to the left side is postponed. So, that is the key word, it is postponed until all the other evaluations in the current time step are completed. So, when the clock pulse comes in, that is the current time step. What are all the different evaluations that have to be there? I need to evaluate 7, 0 and I have to evaluate 15 colon 8. What are the assignments that I have to do? I have to do assignments to 15 colon 8, I have to do assignments to 7 colon 0, right. So, all the right hand evaluations happen immediately and the evaluations are all done in one go, and finally all the assignments happen in one go. So, it is equivalent to evaluating all the right hand side in one place, finish the evaluation and then in one go do the assignments to the left side. So, the operator that you use is called is the less than or equal to token, and the execution of the flow will happen until either the flow itself is over, which means, so I will go and look at this, I will remember the word 7 colon 0, I will go to the next line, that is the meaning of this. I will remember what word of 7 colon 0 had, I will go to the next line. That is the meaning of the non-blocking statement. Again I will remember what 15 colon 8 had, I will go to the next line. At this point I am at the end of this, so but I have remembered what 7 colon 0 and 15 colon 8 are. Now I go and do all the assignments. For 15 colon 8 I should take whatever I remembered in 7 colon 0. So and for 7 colon 0 I should take whatever I remembered in 15 colon 8. So that is the meaning of this. So if you think about this, the hardware equivalent is like this. So the hardware equivalent is, there is a bus that is coming in, right, word 15 colon 0 and word 7 colon 8, right. Because this is inside the passage of clock, there is a register for both of them, 7 colon 0 as well as 15 colon 8, right. So what this does is, at every passage of clock, so this is my actual projected output, 15 colon, oh I am sorry, this is supposed to be 15 colon 8 and 7 colon 0, I am sorry about that, this is 15 colon 8 and this is the projected output 7 colon 0. What this non-blocking assignment does is, it takes 15 colon 8, gives it as input to 7 colon 0 and it takes 7 colon 0 and gives it as input to 15 colon 8. So this is equivalent to swapping the contents of 15 colon 8 and 7 colon 0, and this every clock pulse, this will keep swapping the contents from lower half to the upper half and upper half to the lower half. Let us go back to the picture again. What we have is, we have the values that are there in 7 colon 0 and 15 colon 8, we remembered those values and then we assign them to the left side. So in the picture that I did, it is the outputs of the flip flops. Let us look at the picture again. The outputs of these flip flops or these registers are the ones that I am remembering. I am going to place them as inputs here, but these inputs will get committed only when the next clock pulse comes in. So what you see in this slide is, this one I evaluate all of them on all the things that are there on the right side, and in one go I assign all of these things on the left side, right. So because of that, there is something that is interesting that is happening. So let us look at this always block and this always block. What I have done is, I have taken these two statements and I have swapped the order in which these statements are. So earlier I showed that if I swap the order with a blocking assignment, then either we get a copy of 15 colon 8 or we get a copy of 7 colon 0. Now I established the fact that the left side is actually swapping. I want to now show that the right side is also actually swapping. So let us see logically what the right side is supposed to do. In this always block on the right side, let us look at the assignment statements which are inside there. They are again both are non-blocking assignments. So the way in which non-blocking assignments have to be dealt with is, whenever a clock pulse comes in, I am going to remember 15 colon 8 and 7 colon 0. Once I remember it, I am now at the end of the block. I start from line 1, I look at line 2, I am end of the block. I have evaluated everything on the right side. I go and do all the assignments that are required for the left side. So the requirement required for the left side is, 7 colon 0 needs the previous value of 15 colon 8 and 15 colon 8 needs the previous value of 7 colon 0, because that is the meaning of this blocking, this non-blocking assignment. I want the previous value that was there when the block was entered. So which means this will also do swapping. So if this does not if you are not able to understand this immediately, so go to the beginning of this slide and look at the argument that I made for why this one is swapping. The same argument actually applies for this one. So the key thing is, the order of non-blocking assignments inside an always statement does not matter. So I have two non-blocking assignments here and I have the same two non-blocking assignments, the order is reversed. The logic that is implied from here and the logic that is implied from here are actually the same, whereas if I put it as blocking assignments, the values where the logic is different. So let us see how a simulation queue works. So every Verilog simulation time step is divided into technically actually 4 major queues, but more importantly 3 major queues, the 3 major queues. The first queue, and this can happen in any order. So you have various blocks, right, various always statements, various assign statements, various instantiations and whatnot, right. All of them can execute it in any arbitrary order. This is what is giving you the modeling of concurrency in a digital circuit. So in a digital circuit, all the gates are simultaneously looking at what their inputs are and their outputs will fire, right. So Verilog is essentially modeling that. So in time step 1, in some order of all the blocks, these things are done. Within each and every block, evaluate the RHS or the right hand side of all the non-blocking assignments, evaluate the RHS and change the LHS of all the blocking assignments, evaluate the RHS and change the LHS of all continuous assignments, and evaluate inputs and change outputs of all primitives. This is the order in which various concurrent statements are going to get executed. So let us see this, this is a very crucial thing. So if I am going in time step, so let us say I am at Verilog time step 5 and some inputs have changed, I am going to see what is going to be the output, what is going to be the set of changes at time step 6. Between 5 and 6 we have the so called micro steps, that is what these micro steps are. So at Q1 is a micro step, what it does is evaluate the right hand side of all the non-blocking assignments first. So which means go and take all the values that are on the right side, keep them aside because this may get destroyed later within the procedure itself, it may get destroyed. Keep it aside and evaluate the right hand side and change the LHS of all the blocking assignments, because blocking says I do not have to wait, this statement evaluates the right side and until this is over the following statements cannot execute. That is the meaning of blocking, which means you have to immediately assign to the LHS. Evaluate the right hand side and change the left hand side of all the continuous assignments, evaluate the inputs and change the outputs of all the primitives. Once this is all over, then you go to Q2, which is the second micro step. At this point all the non-blocking assignments will get their left side changed, and finally any display or monitor or strobe statements will print the values. So this is only for printing, Q3 is only for printing. The two major steps are these two, Q1 and Q2. Q1 is all the non-blocking assignments are evaluated and set aside, and the actual assignments happen only in Q2, but before doing that it is done in these things are done. Evaluate the right hand side and change the LHS, evaluate the right hand side and change the LHS of all continuous assignments, evaluate the inputs and change the outputs of all primitives. So let us see the implication of all of these things. I have several examples from this slide onwards. Let us look at this always block. Always at pos edge of clock A equals 1 and B equals 1. If you go by the procedure that I explained before, first of all these two are blocking assignments, right. So because this is a blocking assignment, the meaning of that is evaluate 1 and assign it to A immediately, right. So A is assigned immediately. Once it is assigned immediately, when it is blocking, so once it is assigned only then you can go to the second line. At this point the value of A being 1 is already available, right. So A will become 1 now, 1 plus 1 is 2, so B will get 2. So that is the meaning of this procedural block. So what we have is at time step 0 this procedural block gets executed. At that point this is 1, it gets immediately assigned to this, and since that value is immediately available here, it goes here. So this equality symbol that you are seeing is like in software programming languages when you say equal to, right, whatever you have in 5th line that value should be available in the 6th line, whatever computation you do in the 6th line that value must be available in the 7th line and so on. So it is essentially that block. All the software programming languages, the equality that you see there are all blocking, whereas if you go and look at this one, A is 1 and B is A plus 1. Let us see what the meaning of this is. So because both of them are non-blocking assignments, the first thing that happens is whatever is on the right side that is evaluated first. So there are two non-blocking assignments, which means one gets evaluated, there is really no evaluation that is necessary. So I will have to remember that A should get a value of 1. Then A plus 1 also gets evaluated at the same time. Whatever the current value of A is, you add 1 to it and that should go to B. So if the current value of A is 5, 5 plus 1 should go to B, right. I will remember that. And now I come to the end. At this point I am ready to go and make the assignments. What are the assignments I am going to make? To A, I remembered that I should be assigning 1, so I will put 1. To B, I remembered that I should assign the value 5 plus 1, which is 6, so I will assign 6. So you can see the difference between here and here. Here this block will always give you A equals 1 and B equals 2, whereas here you will get A equals 1 and B equals the previous value of A plus 1. So that is the meaning of the sequential procedural assignment. Let us look at concurrent procedural assignments. In concurrent procedural assignments, what we have is, so in the sequential assignment I have two assignments that are still within a single block, right, within a single always block. Now we are going to reason about what is going to happen across the multiple always blocks. Remember, one always block here, this is supposed to model some circuit, this is also supposed to model some circuit. If I have a statement like this, A equals A plus 1 within one always block and B equals A plus 1 in another always block, let us see what the meaning of this is, right. At time step 0 the clock pulse comes in and I go to the each and every procedure, right, and the order in which the procedure is executed is not suggested by the Verilog standard. Verilog standard does not say anything about if this always block appears in the file before this always block, then do this assignment before this, it does not say anything. So the order of evaluation in concurrent procedural assignments is indeterminate, which means there is some fixed order, but that order is not known to you. Different compilers could do different things, different simulators could do different things and so on. So let us look at this. The order in which this always block will get evaluated has no relationship to this always block, right. At time step 0 you go here, let us say this block gets evaluated first, then whatever the current value of A is, you add 1, and because this is a blocking assignment you assign it to A immediately. And if this always block gets evaluated next, then A has already changed, let us assume, and you are adding 1 to that, again this is a blocking assignment that will go and change B, right. This will happen if this always block is executed before this always block, but because Verilog does not say anything about concurrent procedural assignments, it is possible that this always block gets executed before this always block. If that happened, then B gets the previous value of A plus 1 and A gets the previous value of A plus 1. So both B and A will have the same value, whereas if this happened first and if this happened next, then A will get the previous value of A plus 1 assigned to it and B will get previous value of A before the always blocks were executed plus 2. So it is not clear whether B should use the previous A or the current A. So it is not clear. So in such cases, when you have multiple assignments, right, you have to be very careful. This blocking assignment is not good in the concurrent mode. However, if you do this, in this case what you have done is A equals A plus 1, B equals A plus 1. The model for non-blocking statements is across all the always blocks, look at what is on the right side of non-blocking statements, evaluate them first. So across all of them, if I evaluate A plus 1, it takes whatever is the previous value, add 1 to it. This one is also saying take the previous value, add 1 to it. So this A plus 1 and this A plus 1 are both consulting the same value of A, right. Add 1 to it and keep it aside. We have that, we have the old value of A plus 1 which is kept aside. Now both the always blocks are coming to the end of their respective blocks. At that point you can make the assignments to the left side. So this is our Q Q2. If you look at this picture, right, this is our Q2. Change the left hand side of all non-blocking assignments. At this point, the left hand side here is A is supposed to get 2, A is supposed to get previous value of A plus 1, B will also get previous value of A plus 1. So, A and B are both getting the same value, both of them get the old value A plus 1. So, this is the meaning of what this is doing. So, this is indeterminate. At the end of this, we do not know whether B got previous A or current A and added 1 to it. So, if it is previous A, then we would have added only 1 to it. If it is the current A, it is actually the previous A plus 2. So, we do not know whether B is previous A plus 2 or previous A plus 1, whereas in this one both A and B have previous A plus 1. So, let us look at some of the implications. I am going to ask this question. So, I have the first bullet is supposed to be modeling a combinational buffer. A combinational buffer is one in which the output is supposed to follow the input immediately, and the second bullet is about flip flop. So, what is the correct way to model things? So, the first one is combinational. Let us say there are two ways to do this, right. So, always at in out equals in, always at in out, this is non-blocking equal to in. So, of course, you can always argue that I could have used an assign statement out equal to in, but if we, so this is just an illustrative example, because this may arise in several other places. If you want to model combinational circuits, how do you want to do it, right? So, the way to model combinational circuits is, if I put out equals in, then because of the nature of the assign statement, this in immediately gets assigned to out, which means any change in gets propagated to output, and if out is connected to something else, that will go and immediately trigger the other ones also. Whereas, if I did this one, if I did out less than equal to or the non-blocking equal to followed by in, this would mean I will evaluate in, but I will keep it aside. I will wait for all the other evaluations of the right hand side to get over, and then I will do the left hand side assignments. So, for modeling combinational logic, this is the correct way to do it. Now, let us look at flip flops. So, in flip flops, always at passage of clock Q equals to D, as opposed to Q non-blocking equal to D. So, again, if I use the same argument, the change in D should not appear in Q immediately, right. The change in D is supposed to change as Q in the next clock cycle, right. If that is the case, then changing Q immediately is not correct. Therefore, this non-blocking assignment is the correct way to do it. So, anything that uses Q on the right side should be using the current value of Q, not the new value, whatever is there, right. So, let us say always at passage of clock Q equal to D, and I did something like B equals Q plus 5, right, Q plus 1, right. Let us say I had another statement which was B equals Q plus 1, then is it supposed to take the current D and change it immediately? No. So, whatever value of D comes, it gets assigned to Q. That value of Q is not supposed to trigger anything else yet, because this is a clock statement. Only when the clock assignment is all evaluated, finally you go and make the assignment. So, this Q equals Q non-blocking equals D essentially takes care of the fact that I am sampling D, I am sampling D, and however the assignment to Q, I will do it once all the always blocks are evaluated, and when I am ready to assign to the left hand side of the non-blocking assignments. So, the correct way to do combinational logic is this one. If you are using always statements, the correct way to do combinational logic is this one, and the correct way to do sequential logic is this one. Let us see some of the implications of sequential procedural assignments. So, in this picture we have two different assignments. The statements seem to be the same, except that both the assignments are blocking here and both the assignments are non-blocking here. Let us see what happens because of this. So, always at passage of clock, which means first of all any assignment that happens inside passage of clock means there is a flip flop that is going to be inferred. We are talking about a flip flop. Y1 is not continuously getting in, Y2 is not continuously getting Y. This is not continuous assignment, this is a sequential procedural assignment. If that is the case, only when the clock pulses come in, Y1 and Y2 will change, which means we are modeling with flip flops. So again go back to the Verilog models that I talked about flip flops. I said at passage of clock any assignment that you do inside is supposed to be for flip flops. So let us look at this one now, y1 equals in. So what this means is take in whatever is there, sample it, but because of this equality sign what it says is whatever is in assign it to y1 immediately, and because this is blocking until this y1 copies in, the second line will not get executed, which means the current whatever value y1 got here is available at the right hand side here, and because of, and this is also a blocking assignment, which means this value that you put in goes to y1 and from there it goes to y2. In some sense y2 and y1 are both getting the same values in, right. So if you think about it, it looks like in is given to y1 and y1 is giving its value to y2, but if you go and look at the values that y1 and y2 are getting, both of them are getting the value in. So the circuit that you are going to get is essentially a set of parallel flops. So the way to think about this is each and every assignment gets a flip flop. So y1 is an assignment, y2 is an assignment, both of them get a flip flop, and what is the value that this flip flop y1 is getting? It's getting in. So in goes to y1, so this is y1, and what is the value that y2 is getting? Y2, if you trace through this, it's actually getting in itself. So if you think about that, y2 is also getting in, so it's as good as taking in and giving it to this flip flop y2. So this is y1, this is y2. If you notice, this flip flop 1 and flip flop 2, right, this is producing y1, this is producing y2, they are actually ditto the same, they are exactly the same, right, because that is what the implication is. So the circuit correlates to whatever you wrote as a procedure, and whatever you wrote as a procedure correlates to the circuit. In fact, if you give it to tools, the tools may realize that these two flip flops are taking the same input and giving the same logical value. So if you go on, if you want to optimize the hardware, if you are tapping y1 to do something and y2 to do something, you can as well just tap y1 and get rid of this flip flop 2 altogether. That's what tools would do. Whereas let's look at this one, y1 is non-blocking equal to in and y2 is non-blocking assign y1. Now let's look at the implication of it. First of all, y1 and y2 are assignments, so they require two registers, two flip flops, y1 and y2 are two flip flops. What is the semantic or meaning of this non-blocking equals? So this statement says sample the current value of in, give it to y1 at the end of the clock cycle. Similarly, this one says take the current value of y1 and assign it to y2 in the future, right. So this is sample it currently, give it in the future. This is also sample it currently and give it in the future. So the equivalent circuit is as follows, it's actually a shift register. So the meaning of this one is whatever value is in y1, give it to y2, and whatever value is in give it to y1, but the window in which it's going to operate is controlled by the positive edge of the clock, right. This is going to happen only at the positive edge of the clock. We already know that as a hardware diagram, this is a shift register, right. So this value will be, let's say this value is stable and this value is stable. When the clock pulse comes in, this value will get here, and whatever stable value was here, that will get here, and then the closing window is that rising edge itself, it closes, no further changes are propagated. So the same thing is supposed to be here. So if you want to model it as shift register, you have to do this, whereas if you are modeling combinational logic which is getting registered somewhere, you do this. So in all these cases, right, as an exam question this is a different thing, but as a hardware designer you have a certain intent and you want to express the intent as a program. So if your intent is to want a shift register, then your modeling should also reflect that. A shift register means all the flip flops are sampling their respective inputs at the same time and they copy it to their outputs at the same time. So if you have this respective inputs and to their corresponding outputs, then you are actually thinking, you should think about non-blocking assignments. Whereas if I want a sequence of changes that should result in a change in the output, then you can have a sequence of statements. This is like using temporary variables. In this sense, if you look at this picture here, right, you can as well treat y1 as though it's a temporary variable. In gets to y1 and y1 gets to y2, right. I can as well get rid of y1 and say y2 equals in, because it's blocking assignments. So whenever you want some temporary things, if you have a very large expression on the right side, you want to break it down into smaller ones, then this is a good thing to do. So let's look at if the same thing is done concurrently. Here what we have is y1 is in and y2 is y1. We have it in two different statements, and this is done concurrently, which means it's not in the same always block. There are two different always blocks, right. So the key thing is, if I do this, always at passage of clock y1 equals to in, that means infer a flip flop for y1. So that's this flip flop, this y1 is supposed to follow in. Always at passage of clock y2 equals y1. So that means this flip flop y2 is supposed to be copying y1, but because of the semantics of these always blocks and the blocking assignment, so if this block got executed before this block, then whatever value was in would have propagated to y1, and that value of y1 will get propagated to y2, which means the current input will go to y2 also. So that means it is equivalent to this parallel flop case. So the input is going to both y1 and y2, or if this block gets executed first, then y2 makes a copy of y1 and then y1 changes to in. That would be equivalent to doing the shift register. So y2 takes the value of y1 and y1 takes the value of in, right. So this is crazy. If we put blocking assignments, because the order in which the always blocks are going to be executed is not guaranteed, then there is a race condition on the input of this flip flop y2. It could either be in or it could be y1, and you don't know which. A single compiler will always give you the same result, but if you take it to a different compiler, it may actually give a different result. So this is a serious problem. Whereas if you had this statement, these are concurrent procedural assignments again, because they are two always statements. We have both of them with non-blocking assigns. So no matter the order in which it's done, we'll have to wait for all the left hand sides to be evaluated first, and once all the evaluations are over, only then you will do the assignments. So whether it's this always block or this always block, right, you do the evaluations first. So which means take the current value of in, keep it aside, take the current value of y1, keep it aside. Whether this executes first or this executes first, both of them have to execute, and once they are done, once they come to the end, only then you go to the left side. In the left side it says whatever value of in you remembered, put it in y1, whatever value of in y1 you remembered, put it in y2. So that is equivalent to the shift register. So the shift register could either be modeled like this or modeled like this, whereas if you do this, this is actually still a correct circuit, there is no problem, only that both y1 and y2 will get the same value, right. However, this circuit is incorrect in two ways. One, there is a race condition, and two, the intent of the programmer is not going to be captured, right. So if the intent of the programmer is make two flip flops y1 and y2, which are both supposed to follow input, that's not captured. If the intent of the designer is, oh, I actually need a shift register, even that is not captured. So this may actually depend on the tools that you are using for simulation. So this is a terrible thing. So this is the reason why you don't use this blocking assignment statements for sequential logic. Whenever you want a flip flop, you always use non-blocking assignments. So combinational logic generally use blocking assignments, sequential logic generally use non-blocking assignments. The only exception for this case is, do not use a non-blocking assignment if another assignment in the procedure requires a new value in the same step. What I mean by that is, if you are using something for a temporary calculation, use blocking assignments and not non-blocking assignments. So let us see examples. So I am going to mix different kinds of statements from now on, and the rest of the video is about this. So, let us say this, I have assign A equals 3, right, it is all in always statement, blocking assign A3, blocking assign A4, blocking assign A5, blocking assign B equals A, and I say now wait for 5 time units. That is what the meaning of hash 5 is. Let us see what the meaning of this part is first. So, it says A should immediately get the value of 3, the next line says A should get immediately the value 4, next line says A should get the value immediately 5, and B equal to A says whatever is the value of A immediately I should give it to B. So, at this point this A equal to 3 and A equal to 4 actually do not do anything, you are destroying the value of A making it 3, you are destroying that value and making it 4, you are destroying that value and making it 5. So, B will be 5, A will also be 5 at the end of time 5 units. That is for this case. Let us see what happens here. A equals 3, A equals 4, B equals A and A equals 5. So, if I go and do this in a sequential programming language, you would expect that B gets the current value of A. What is the current value of A? According to this statement, the most recent one is the assignment of A is 4. So, B will get 4 and A, there is another assignment later, this is assigning 5 to A. So, at the end of this assigned statement, this always block, B will get 4 and A will get 5, right. So, changing the order of these assignments has actually changed the values that A and B will get. Now, let us see this part. So, what we have done here is this last statement is replaced by a non-blocking assignment, and this B equal to A is replaced by a non-blocking assignment. So, let us see the implication of that. In this case 3 gets assigned to A and that comes here at this, and the line, the control goes to the next line. There you do not care about 3, you assign 4. When you come here you do not care about 4 also, you now assign 5, and that current value of 5 is assigned to B. So, B gets the value 5 and A gets the value 5 also, but A has it immediately and the value 5 for B is scheduled for the future, which means this 5 is remembered, and if there are other non-blocking assignments, all of them should get evaluated and only then you will assign it to B. Let us see what happens on the right side here. So, this 3 and 4, this 4 destroys 3. So, that is straightforward, 4 destroys 3. Then this value of 4 is supposed to be copied to B, but not immediately, sometime in the future. So, B is going to get the value 4 sometime in the future, but A is assigned 5. So, the key question is B supposed to get 5 or is B supposed to get 4? So, at the time of execution of B, we said remember the value 4, this is going to be assigned to B in the future. So, even if A changes, we said remember the value 4 for B. So, at the end of this always block, B will get 4 and A will get 5. So, for the left side A equals 5 and B equals 5 for both the cases, for the right side A equals 5 and B equals to 4 for both the cases. So, this is just to show you some more, give you some more understanding of blocking and non-blocking. In this case we are mixing blocking and non-blocking assignments, and here there is no implication of a flip flop or anything because there is no always at pos edge of clock, right. It is supposed to be a combinational block with some delay. This 5 is 5 units of delay. Let us look at these two always blocks, right. So, A equals 3, A equals 4, B equals A. So, it is clear that B is supposed to get a value of 4, then A equals 5. So, at this point A becomes 5 and B equals A. At this point B also becomes 5. So, this B equal to A is an immediately assigned here. So, this is blocking. So, B gets 5 here immediately, A also gets 5 here immediately. At this point when you come here B equals to 5, B equals to A equals to 5. In fact, this whole thing is as good as these 3 statements did not exist, because this is the last assignment to A and we are taking the last assignment of A and assigning it to B immediately, which means all these 3 statements, even if they were not there, the meaning is the same. Let us look at the piece of logic below this. So, A equals 3, A equals 4, B equals A. So, at this point B is supposed to remember the value 4. We are still within the same procedure. A gets 5, right. So, this 5 is not supposed to reflect in B, and here this A equal to 5 is again blocked here. So, this is a blocking assignment, A equals to 5. So, this B equal to A is actually looking at the right side, which got immediately evaluated to 5. So, let us look at the sequence of events here. So, all the blocking assignments are done one after the other. So, this blocking assignment is 3, this blocking assignment is 4, you hit a non-blocking assignment. At this point what we do is we will schedule B to get a value of 4 in the future and we continue, right. That is the sequence. A gets 3 immediately, A gets 4 immediately, B gets a value of 4 to be scheduled in the future. I continue running this, A gets a value of 5, and this one says schedule a value of 5 for B in the future. So, in some sense this one says assign 4 in the future and this one says assign 5 in the future, which means of the two events, whether 4 is in the future or 5 is in the future, the program order says 5 in the future is what I want, because 4 in the future is coming before 5 in the future. At the end of this statement B will also get the value 5. So, this one and this one will actually get the same values. So, this is not good for modeling hardware, but again I am showing this so that you understand the notion of blocking and non-blocking and the problems with mixing. So, A and B both of them get 5 in both the cases. Let us look at these statements now. A equals C, A equals D, A equals E, right. So, I have 3 non-blocking statements. First one is trying to assign C to A, the second one is assigning D to A, and third one is assigning E to A. So, in time step 0, we are saying that schedule C for A in the future. Again at time step 0, we are still evaluating the right side, we are saying assign D to A in the future. Again at time step 0, we are saying evaluate E and assign to A in the future, right. So, what this means is there are 3 different assignments that we are trying to do to A in the future. The last assignment to A prevails, which means A will get the value of E, and this one it says B equals A, right. What this does is B is trying to get the, so you go and look at the evaluation of A. When you evaluated A, all these events for A are scheduled in the future. So, whatever is the previous value of A, take that, immediately copy that to B. That is the meaning of this statement, right. So, the meaning of this whole thing is take C, D and E, this assignment C and D do not matter, the assignment E should be given to A in the future. However, whatever is the current value of A, assign it immediately to B. That is the meaning of this block. Let us see what happens here. There are C and D here, right, and you are sampling A. What is the A that you will be sampling here? The A that you are sampling is whatever you entered the block with, right. So, this B equal to A does not really change anything. This B equal to A is still sampling the old value of A, because the other assignments to A are all non-blocking. So, if it is all non-blocking, you can as well go and execute this first. When you execute this first, A is taking the value whatever the previous value is, you schedule that for B immediately, and this A equal to E is again scheduling something in the future. So, this A equal to E overrides this A equal to D and A equal to C. So, A will get the value of E and B will get the previous value of A. So, that is true for both these things. Let us look at what happens here. So, A equals C, A equals D, A equals E, and this means whatever is the current value of E, assign it to A in the future, and whatever is the current value of A, assign it to B in the future. That is the meaning of this, and the meaning of this one is C and D, right, of C and D, D is the latest assignment. So, since all of these are non-blocking assignments, right, you take the last assignment for each of these ones. So, the last assignment of A is take E, the last assignment of B is take A. So, whatever the current value of A is, give it to B, whatever the current value of E is, give it to A. So, all of them are actually doing the same thing. So, A of t will become E of t and B will become E of t minus 1 in all cases, because B is copying A and A is copying E. So, B will be lagging behind A in one step. So, A of t will be E of t, whatever the current value of E is, you will get it immediately to A, but B is copying the current value of A, which means it is the previous value of B. So, A of t is E of t and B of t is E of t minus 1 in all these 4 cases. So, clearly you can see that mixing the statements is equal to and non-blocking equal to, it is already getting very confusing, right. You have to remember so many details about what each of these things are and so on, right. So, there is some non-determinism that happens with respect to how these things are going to execute, but that does not matter, all of them give the same results. Let us do one final round of mixing statements. So, you have A equals C and A equals D, then you have B equals A equals E, and then we have one more assignment to B here, right. So, there are 2 assignments to B. In this previous slide, we had only 1 assignment to B and 3 assignments to A. In this slide, we have 3 assignments to A and 2 assignments to B. Let us see how to reason this. So, A equals C, A equals D, which means A equal to D overrides A equal to C, and this B equal to A is actually going to look at the old value of A. So, this is not going to look at the new value. So, this is the old value of A. This E is also scheduling something for A in the future, right. So, this A equal to E is not really doing much. So, this C, D and E, A equal to E overrides D and C. So, this A equal to E is also scheduled for the future. So, which means I can, this is non-blocking, I can come to A. So, it is again saying B equal to A. So, in some sense B equal to A and B equal to A are the 2 statements that we have, and which means B is going to copy A and A in the future is going to take the current value of E. That is the meaning of this always block. So, I recommend that you go and reason what should be the assignments for each one of them. I will give you what the final assignment must be. So, A of t must be equal to E of t and B of t must be equal to E of t minus 1 for this side, and for the right side A of t must be equal to D of t minus 1 and B must be equal to D of t minus 2 in these cases. So, now that you have some understanding of blocking versus non-blocking, I showed you what happens to the left side. I want you to go and think about what happens to this one and this one. So, clearly all this mixing and matching, as a programming technique I can do all these dirty things, but as a designer this is a nightmare. So, if an engineer who is working under me wrote anything like this, I would immediately fire the engineer, because this is okay to learn what non-blocking and blocking assignments are, but this is not capturing the intent of the designer neatly, and anyone else who is going to look at it is going to get confused. So, the thumb rules are that use blocking assignments only for combinational logic, use non-blocking assignments only for sequential logic, and as much as possible do not mix non-blocking and blocking assignments. So, in general what you do is you keep the combinational blocks aside, you keep the sequential blocks aside and you combine them, you have them as 2 different always blocks. This is exactly what we did in our state machine. If you go back and look at the state machine's Verilog code, you would see that the sequential logic was one single assignment and it used non-blocking assignment, and the combinational logic were 2 different blobs, and the combinational blobs were separated from sequential blobs. They were different and these were different, right. So, this brings me to the end of module 46. In the next module what we will do is we will learn the notion of pipelining. So, in pipelining, we will, all the concepts that we learnt about the blocking and non-blocking assignments, we will take that and see what is the implication of pipelines. So, this brings me to the end of module 46 and I will see you at module 47. Thank you and see you soon.